Welcome to Bright Ray Academy, where the future of radiology students will be as bright as rays. I am super thrilled to be your guide for this explainer on screen-film radiology. Let's just jump right into it. To all of you incoming students joining the cohort today, seriously, a huge, warm welcome to you all. We're embarking on a genuinely fascinating journey in this explainer. We're going to set the stage for understanding the exact, almost magical path of an invisible X-ray photon as it transforms into a visible, life-saving medical image. Okay, let's look at the syllabus and systematically deconstruct exactly how we capture these medical images. We're covering film anatomy, intensifying screens, the latent image, screen characteristics, and finally, handling and storage. All right, Section 1, film anatomy, specifically the base and the emulsion. We'll start by examining the macroscopic physical objects you are going to be handling every single day in the clinic. You can think of the anatomy of radiographic film as, well, essentially a microscopic sandwich. You've got this thick base right in the middle, and that provides your mechanical support. Then, bound to it by an adhesive layer is the absolutely crucial emulsion layer. And the whole thing is capped off by a protective overcoat just to prevent any scratches. Now, most X-ray film is what we call double emulsion film, meaning it actually has these layers on both sides. This emulsion layer is the absolute heart of the radiographic film. It's a homogeneous mixture consisting of two main components. First up, high-quality gelatin. It's kind of similar to dessert gelatin, actually, but clear so it transmits light and porous enough for processing chemicals to easily penetrate it later on. Second, suspended right there in that gelatin are silver halide crystals. These crystals are the active ingredient. This is where the X-rays or light photons actually interact. Now, here is a truly startling statistic for you. The crucial point here is that less than 1% of X-rays incident on radiographic film actually interact with it to form an image. Seriously, less than 1%. So using film all by itself to detect X-rays, it's highly, highly inefficient. Which, of course, brings up a really vital question. So how do we actually get an image without exposing the patient to massive doses of radiation? I mean, if we just use direct X-ray exposure on the film, the patient dose would be completely unacceptably high. This leads us to a massive efficiency problem, one that requires a bit of a technological superhero solution. And that brings us to Section 2, radiographic intensifying screens. These are our amplifiers. To solve that dose problem we just talked about, we sandwich the film between intensifying screens that act as incredibly powerful amplifiers. A typical intensifying screen actually has 4 layers, but the real magic? That happens in the phosphor layer. This active layer absorbs the X-rays and then glows brightly, emitting visible light. So it's actually this emitted light that primarily exposes the radiographic film, amplifying the effect of the X-rays tremendously. When we compare these methods side by side, we can clearly see the high stakes of our imaging choices. With direct exposure film, you get a highly detailed image, absolutely, but it comes at the steep cost of a very high radiation dose. On the flip side, with screen film combinations, we accept a slight image blur because it allows us to drastically protect our patients from unnecessary radiation. And honestly, modern screens are so good today that this slight blur is usually not a serious issue at all. Okay, moving on to Section 3, forming the latent image. This is where the microscopic magic happens. We're transitioning from the physical cassette right down to the chemical physics of those silver halide crystals we mentioned earlier. Let's define what actually happens during exposure. A late image is the invisible change induced in the silver halide crystal. You see, immediately after exposure, the image is entirely invisible to the naked eye. It exists only as stored chemical potential energy within the film emulsion, just waiting to be unlocked by chemical processing. Now, a key structural feature of the silver halide crystal is what we call the sensitivity center. You see, these crystals aren't actually perfectly structured. They contain chemical contaminants, usually silver sulfide, that get introduced during the manufacturing process. This specific imperfection is the sensitivity center, and it's the exact location on the crystal where the latent image will eventually form. Let's break down this microscopic cascade step by step. First, light from the screen interacts with the crystal, releasing electrons. Second, these electrons migrate and get trapped right at that sensitivity center, giving it a negative charge. Third, positive silver ions within the crystal are attracted to this new negative center, where they neutralize and form atoms of metallic silver. Ultimately, this entire process deposits between 4 and 10 invisible atoms of silver right at the sensitivity center, creating our latent image center. Moving right along to Section 4, Screen Characteristics. We're looking specifically at speed, noise, and resolution here. Let's step back up to the macro level for a second and look at how different screens actually perform in a real clinical environment. Modern rare earth screens achieve significantly higher speeds than the older calcium tungstate screens used to. They manage this by doing two things: absorbing more X-rays, which we call detective quantum efficiency, and then emitting more light photons per X-ray absorbed, which is known as conversion efficiency. Rare earth screens, which are made from elements with atomic numbers 57 to 71, well, they are the gold standard today. Their higher DQE and CE make them incredibly fast. But, there is a catch. Because they emit specific spectrums of light, these advanced phosphors require you to use specific, deeply red safe lights in the darkroom. If you try to use a standard safe light, you're going to fog the film and completely ruin your image. And there's also a bit of a trade-off for all this amazing speed. Higher speeds can actually increase quantum model noise, which kind of looks like a speckled, grainy background, and it can reduce our spatial resolution, meaning our ability to image tiny objects clearly. But this slight loss in detail, it's the necessary trade-off we have to make to achieve those drastically lower patient radiation doses. Finally, we've reached Section 5, Handling and Storage, because all of this incredible physics and chemistry means absolutely nothing if we don't care for the physical media properly out there in the real world. Radiographic film is a highly sensitive radiation detector. You must strictly adhere to these environmental rules in the clinic. Film has got to be stored below 20 degrees Celsius or 68 degrees Fahrenheit because excess heat increases base fog and it reduces your contrast. Humidity, that has to be kept right between 40 and 60%. Too much humidity causes fog, but too low humidity, that can actually cause static electricity artifacts right on your image. And of course, complete and total darkness is required until processing. Now, physical handling is just as crucial as the environment. Because the film is highly pressure sensitive, improper handling causes physical artifacts. You must literally never bend, crease, or scratch the film or the screens inside the cassettes. Clean hands are an absolute must here, and hand lotions should be entirely avoided. Honestly, even a tiny fingernail scratch or a little smudge of hand lotion can completely ruin a radiograph and obscure a really critical medical diagnosis. So, I want to leave you with this final thought. When you process your very first film, will it reveal a clear, life-saving diagnosis, or will it just show a darkroom artifact from rough handling? Remember, the future of this complex technological magic, this really beautiful chain of physics and chemistry, rests entirely in your careful hands. Thank you so much for joining me on this explainer, and I will see you in the next one.